Namaskar, hello, once again a very warm welcome to CIET NCERT's live phone and interactive program. I am Tanvi Khurana and all the students who are studying in class 12th, this is a chemistry class for all of you. And the topic that we are going to discuss today is coordination compounds. So, we will be discussing what all coordination compounds are and a lot more related to it. If you have any questions, any queries, please feel free to reach out to us. Either you can give us a call on our number, that is 8800440559, or you can email us. The email ID is dth.class12@ciet.nic.in. Apart from this, either you can message us on our YouTube channel, that is NCERT Official, where you are watching us live and you can write down your questions in the live chat box, or you're watching us on PME Vidya channel number 12 as well. And all this information is being given to you in the form of ticker, and throughout this program, this information will be there on your screens. So, please feel free to give us a call. And apart from this, let me please introduce you to our sign language interpreters that we have for this particular program. We have Neetu and Rimpi, and they both are going to stay with us throughout the program. Let me please welcome our guest for today. We have with us Dr. Rajesh Kumar Sharma. Sir, a very warm welcome to you.
Thank you.
Thank you. Sir is a Ph.D. from IIT-Gate, and he is having more than 15 years of teaching as well as research experience. So, let's just get to know the particular topic, coordination compounds, and let's just begin with the simple definition of this title, coordination compounds. Sir, would you like to tell us that what exactly are these compounds, and if you can explain it with the help of some examples, that would be better.
Yeah. When we talk about coordination compounds, it means that one metal from the D block that will be present in the center, and that metal has the vacant orbitals, especially in case of transition metals when it provides D subshell orbitals empty, and one atom of group of atoms that will make coordinate bond with the metal. Such kind of compounds to be referred as coordination compounds. Like that, one kind of central metal will be there, and surrounding metal atoms or group of atoms which will surround to the central metal and will form a sphere like that structure. Central metal will be surrounded, different kind of groups will be present. In that case, the compound will form. We can look at here in this here one kind of central portion of the cube, that is metal, and surrounding sphere, that is called ligands, providing lone pair of electrons. Basically, we can say that complex chemical compounds featuring a central metal atom or ion bonded to surrounding molecules or ions, generally called ligands, via coordinate covalent bond. Coordinate covalent bond means both electrons of the bond to be provided by one atom of group of atoms, forming a stable structure that often retains its identity in solution, unlike simple salts. We can have an example including biological molecules like hemoglobin, that composed of iron metal, vitamin B12 made up of cobalt, and chlorophyll that is made up of magnesium. These all are examples of coordination compounds in which central atom is surrounded by different donor atoms. So, we can look here. Here one is the central atom, that is cobalt, having atomic number 27. This metal provides empty orbitals to the surrounding molecules. It may be single atom, group of atom, or charge or neutral species that having extra electrons will provide pair of electrons to the central metal. In this case, cobalt is central metal and surrounding spheres, that is called ligands, providing coordinate bonding to the central metal. Here we can say that one kind of donor atom is nitrogen, or we well know that nitrogen having one lone pair, So, this lone pair will be provided by the nitrogen to the central metal cobalt. In similar case, Cl is also providing, forming a complex kind of structure. So, this will be the presentation of a coordination compound or coordination complex, we can say that.
Sir, you have used a term ligand.
Yeah.
Would you like to tell us what exactly does it mean, and if you can cite a few examples?
Yeah. Ligands means donor atom. It may be single atom, group of atoms that having extra electron density, extra electrons, and provide electrons to the central metal and joined by the special kind of bond that is called coordinate bonds. So, simply we can say that the atoms of group of atoms that provide pair of electrons to the central metal generally referred as ligand. Like here we can say that in case of whatever we are seeing on the screen right now, NiCl2, H2O whole 4, here is chlorine atom and water molecule. Both are acting as a ligand because these are providing pair of electron to the central metal nickel. So, we can have examples of ligands, and we can talk about some key terms related to the coordination compounds. First, we are coming on central atom or ion. Generally, when we talk about central, central means the central will be present, the atom will be present in the center, surrounding by the donor atoms. Central atom or ion to which a fixed number of ions or groups are bound or bonded by coordinate bond. Here NiCl2 H2O whole 4, nickel is the central metal and chlorine and water, that is called aqua, is acting as ligand. Nickel providing empty orbitals and chlorine and water is donating to electrons and joining by the coordinate bond. So, in this complex, nickel is central metal atom. Next, that is ligands, electron donating species, ions or molecules bound to the central atom in the coordination entity. These may be charged or neutral, but must have higher electron density. When we talk about the types of ligands, that means unidentate, bidentate, tridentate, tetradentate, polydentate. Uni means single, dentate means donor. We can say that in case of unidentate, it is a ligand which has one donor site. It will give 2 electrons to the central metal atom. The ligand bound to metal ion through a single donor site. We have an example like that, H2O and NH3. If we talk about H2O, central atom is oxygen and having 2 lone pair of electrons, and it can donate 1 pair of electrons to the central metal, and in case of NH3 that having 1 lone pair also. So, these both are unidentate ligand. When we talk about bidentate, it is the ligand which have 2 donor sites. It means that single ligand will donate electrons from the 2 sides to the metal. That is why bidentate. Bi means 2. Dentate means denticity. It is just joining with the 2 sides to the central metal. We can have example like that, oxalate ion. Oxalate ion having COO negative and COO negative. Oxygen having more electron density and negative charge. In similar way, both oxygen having negative charge, and these oxygen will donate pair of electrons to the central metal. Another well known example, that is called EN or ethylene diamine. Generally it just comes in many times in examinations also. If we talk about like complexity, then this kind of ligands generally comes in that. So, this one is the ethylene diamine. or we can say 1,2-ethane diamine, didentate or bidentate ligand, because having 2 nitrogen atom, and both nitrogen atom donates pair of electrons to the central metal. So, this will be the example of bidentate ligand. Moving further, we have the polydentate ligand also. It is the ligand which have several donor sites. Well known example is EDTA, that is 4 minus. It will be ethylene diamine tetraacetate, EDTA, complexing ligand is there, ethylene diamine tetraacetate, having 4 acetate groups, that to be donate electrons, and 2 nitrogen atom also present in there. So, it will donate 6 bonding sites to the metal atom, that is why it will called hexadentate ligand. In case of ambidentate ligand, ambi means from the both sides, like that if I have this one, if it is acting as a ligand and this one is the central metal. So, this is monodentate ligand having 2 donor sites, one from here, another from here, but once it will join by 1 bonding sites. Ambidentate, like this one is metal, coordinate bond is forming, 2 donor sites. From here I can also donate, make the bonds, but by another site this is also donor atom. This can join with the central metal, but once 1 atom will be donates. So, in case of ambidentate ligand, monodentate ligand which can ligate through 2 different sites like NO2 and SCN minus. In case of NO2, nitrogen is also donor atom and oxygen is also donor atom. In case of SCN, sulfur also is donor atom and nitrogen is also donor atom. But both will donate once at a time, only 1 atom will bond to the metal, but it having the capacity to donate from any of the atom, both atom having the capacity to donate pair of electrons to the metal. So, ambidentate ligands to be there in similar way. If we talk about
4 types of ligands we have already discussed,
Yes,
and
yes,
there's
ma'am.
another type called chelating ligands. Are they any different from the other 4 ligands that we have discussed so far?
There is a little bit difference.
Okay.
In case of we talk about monodentate ligands, that means that to be bonded by 1 bonding sites only. In case of bidentate, it will bond by 2 sites, tridentate 3 sites. But one kind of ligands that surround the metal from the surrounding sphere, that will make a surrounding sphere central metal, and the ligands will make kind of bonds and it will surround the metal from the surrounding from all over the sides, that will make a ring kind of structure. Such ligands which make a ring kind of structure surrounding to the central metal, that is called chelating ligands. Like we can talk about ethylene diamine, this is one kind of chelating ligand. Oxalate is also there. So, in case of chelating ligands, when a bidentate or a polydentate ligand is attached through 2 or more donor atoms to be the same central metal ion to form a ring structure, ring kind of structure will be formed. Chelates, that means coming from the crab's claw, it means that the claw will surround 2 like that. Ligand and the complex forms. In case of this one, Cu, that is NS2, CS2, CS2, NS2, ethylene diamine having 2 positive charge, that is called chelate ion. Here we can look this one, copper is the central metal and 2 ethylene diamine ligands surrounding to the metal copper and forming a ring kind of structure here. So, this will be the chelating complex or chelating ligands and it having ion. So, it will also called chelate ion.
So, there's a term called coordination numbers. Would you like to tell us what are they and any examples along with it?
Yeah. Coordination number means how many ligands are attached by coordinate bond. It means that how many coordinate bond to be made or provided by the ligands to the metal atom. The total count of these coordinate bonds generally called coordination number. On behalf of that, if we talk about monodentate ligand, it means that they will make only one coordinate bond. So, its coordination number will be 1. In case of bidentate, coordination number will be 2. In case of tridentate, coordination number will be 3. We have taken one example, that was EDTA. This single ligand will make 6 bonds with a central metal. So, its coordination number will be 6. That is why EDTA was called hexadentate ligand. Like in case of chelating ligands, that having the more tendency to make multiple kind of coordinate bonds. Coordination number, the number of coordinate bonds formed by central metal atom with ligands. Example, in the complex ion, we have one example, that is CuNH3 whole 4 plus 2. Here we can see that 4 NH3 or 4 ammonia ligands are attached to the central metal ion, that is copper. Hence, the coordination number of Cu2 plus ion in the above complex will be 4. We can look at the picture. Here is the 4 coordinate bond. Central metal copper is shown here, and the coordination 4, that means generally forms tetrahedral geometry or square planar geometry. It means that the complex which have coordination number 4 or coordination number 4, that will show 2 types of geometry. One is tetrahedral, another is square planar kind of complex to be formed. So, coordination number play a significant role in coordination chemistry. It will decide the stability of the complex also. If the number of bonds will increase, the complex becomes stable and its enthalpy of breaking of its bond will be increased. So, stability constant of the complex will also increase and the complex will be more stable. It means that coordination number will be increased, stability of the complex will also increase.
So, after coordination number, there is another term called oxidation number of this complex. Is it different?
It is slightly different from the coordination number, because when we talk about coordination number, oxidation numbers like that, the charge which is present on the metal. We can talk about oxidation number. The charge of the complex, if all the ligands are removed along with the electron pairs that are shared with the central atom. We can have an example again, CuCN whole 4 3 minus. The charge on the complex will give the oxidation number. So, in case of oxidation number, we can mind the charge on the complex and the ligand which is present inside the sphere, and by the simple calculation we can calculate the oxidation number of central metal atom. In case of CuCN4 3 minus, Cn ligand is having -1, that means Cn single minus will be there. In this complex, we talk about CuCN4, that is 4 minus is equal to -3. We can just make simple equation x minus 4 is equal to -3. In this complex, we are just calculating the oxidation number. Then x will be equal to 1. Oxidation number of copper in this complex will be 1 and represented as Cu1, generally oxidation number. When we are going to give IUPAC name to the coordination complex, then there is a rule to write the oxidation number of the central metal in kind of bracket, that will show its oxidation number. and metal having different, especially in case of transition metals, will show different oxidation states. That's why the complex forming tendency of transition metals is higher. Whenever central metal will join with the ligands, then coordination sphere will form. So, in case of coordination sphere, the central ion and the ligands attached to it are enclosed in square bracket, which is known as coordination sphere. The ionizable group written outside the bracket, that is called counter ions. We can have example AgCN whole twice negative. This square bracket inside area, that is called coordination sphere. So, next is coordination polyhedron. The spatial arrangement of the ligands atoms which are directly attached to the central atom or ion define a coordination polyhedron about the central atom. Most common coordination polyhedra are octahedral, square planar, tetrahedral. In coordination chemistry, generally these three kinds of geometry to be seen. Whether it will be complex, will be octahedral, square planar and tetrahedral. In case of coordination number 6, geometry will be octahedral. In case of coordination number 4, geometry will be square planar and tetrahedral. We can have one example here, that is CONH3 whole 6 3 plus is octahedral. We can look at here, NH3 is 6, coordination number is 6, from here we can catch it. Coordination number 6, geometry will be octahedral. Coordination number 4, we have to look about the nature of the ligand. Ligand will decide whether it is going to be tetrahedral or square planar. Generally, strong ligands gives square planar geometry and weak ligands gives tetrahedral geometry. But in case of NiCO4, while having a strong ligand, but due to non-availability of the empty d orbitals in nickel, so it will show the tetrahedral geometry with the sp3 hybridization. And PtCl4 2 minus, we know that chlorine is weak ligand, so it will form like that PtCl4 square planar complex, NiCO4 will be tetrahedral. Now, homoleptic and heteroleptic complexes. Complexes in which a metal is bound to only one kind of donor groups. That means all the ligands will be same. CONH3 whole 6 3 plus. 6 NH3 is joined with the central metal atom cobalt here. All the ligands are same, so that will call homoleptic complex. And complex in which a metal is bound to more than one kind of donor groups. That means different ligand will be there in coordination sphere. If the different ligands are there in coordination sphere, that means the complex will call heteroleptic complex. We can have one example, CONH3 whole 4 Cl2. Here two types of ligands are there. One is amine, that is NH3. Second is chlorine. Two types of ligands are present in coordination sphere. Such kind of complex to be called heteroleptic complexes. To making it more clear, the components of coordination compounds we can just look at here. We have taken one complex, that is K4FeCN6. K4FeCN6, that is potassium hexacyanoferrate. The potassium, that is simple ion, to be known as counter ion. The species which are written outside the brackets generally are called counter ions. If it is positive species like that potassium metal, it will be written in the left hand side. and the negative kind of counter ion is coming, negative ion is coming, that to be written in the right hand sides generally. So, here potassium is simple ion or counter ion, iron is the central metal atom, and Cn is the ligand. 6 Cn are joining. So, this 6 will represent coordination number, and the overall that to be called complex ion. So, yes.
Here you have written potassium K4 as simple ion or counter ion.
Yeah.
So, are these the same terms?
Yeah, simple ion that is having only one valency, and generally just this potassium is coming to fulfilling the charge of the complex, because FeCN6 will be showing the charge to just making it neutralize. The potassium ion will be coming.
Okay.
So, that is simple ion just coming outside the square bracket and does not forming the coordination sphere. But in the case of Cn, it is a ligand, it will form kind of coordination sphere.
So, simple ion and counter ion are the same things.
Simple ion, counter ions are the same things.
Okay.
We can just simple manner we can understand, both are coming outside the bracket, generally termed as counter ions. Chlorine also coming outside the bracket. If it is coming outside the bracket, it will behave like counter ion.
Okay. And there's another term that we known as double salts.
Yeah.
Would you like to tell us more about it along with the example?
Yeah. Generally, double salts contain a combination of two salts. When we talk about double salt, that having combination of kind of two salts will be there. These are the addition molecular compounds which are stable in solid state, but dissociate into constituent ions in the solution. Examples are like we have example carnallite, KCl 1 salt, MgCl2 2 salt. It means that there is a combination of two salts, one KCl, second is MgCl2. That is why these are called double salts, and 6 water molecules are going to be associated. These water molecules are generally termed as water of hydration, that is water of crystallization, that is 6 H2O is coming. In case of next complex, that is we double salt example more salt, FeSO4, NH4 whole twice SO4. FeSO4 is one salt combining with the another salt, that is NH4 whole twice SO4. So, there is a combination, that is why these are called double salts. These are different from the coordination compounds.
Would you like to tell us more about the difference between double salts and coordination compounds?
We just are taking the example. In case of potassium alum, that is also one kind of example of double salt, that is K2SO4, Al2SO4 whole thrice, and 24 of H2O, that is water of crystallization 24 of H2O. And when we talk about difference between double salts and coordination compounds, generally coordination compounds having coordinate bond, and when drop in the solution, its coordination identity will not to be disturbed. But in case of double salts on solutions, it will just ionize and giving different kind of ions. There is no such kind of coordinate bond present in double salts. To making it more clear, we can talk about the difference between salts and coordination compounds. In case of double salts, these exist only in solid state and dissociate into constituent species in their solution, like KCl to be dissolved, K positive, Cl negative will be there. But in case of coordination compounds, they are retain their identity in solid as well as in the solution state. When coordinate compound to be dissolved in the solution state, it will dissociate and give counter ion will make the different charge, and remaining coordination sphere will make the different charge. Like in case of K4FeCN6, we can take example of K4FeCN6. When it going in aqueous form, dissociate, potassium will becomes positive, and one complex that is FeCN6 that will make the negative. So, FeCN6 coordination sphere will not to be disturbed in solution state in case of coordination compound. But in case of double salt, we can talk, they lose their identity in dissolved state. Coordination compound, they do not lose their identity, as we have just discussed right now. They do not lose their identity. FeCN6 is not losing its identity in dissolved state also. Their properties are essentially the same as those of constituent species. Their properties are different from those of their constituents. For example, K4FeCN6 does not show the test of Fe2 plus and Cn minus ions separately because the ions has been not generated. In case of FeCN6, Cn negative ion will not furnished by this complex because it has made coordination sphere already by coordinate bonds. It becomes some kind of stable. Only positive ions, that is in form of potassium, will be furnished. That is why we are telling here K4FeCN6 does not show the test of Fe2 plus and Cn minus. But in case of KCl, like we talk about, that will give plus K plus ion and Cl negative ion. The test for Cl negative ion and K plus ion both can be tested. In case of double salts, the metal atom ion exhibit normal valency. But in case of coordination compounds, the number of negative ions or molecules surrounding the central metal atom is beyond its normal valency, because the central atom generally metal from the transition, it may be from the inner transition also, but inner transition metals having less tendency to make the complex formation. So, empty d orbital will be available by the ligands, and according to the types and charge of the ligand, metal will becomes flexible. It can just accommodate and provide the empty orbitals by the reorganization or intermixing of its d orbital with the s and p also. That process generally called hybridization. It means that when metal is approaching or coming in contact with ligand, or we can say that when ligand is approaching to the metal, metal will provide empty orbiter accordingly what kind of complex is being formed. So, in the series we are moving further and taking some kind of nomenclature of coordination compound. We will talk about its rules, regulations, and we will have some examples to make the concept clear, and we will be able to nominate the compounds of coordination according to the IUPAC system. Before starting, one point we must notate that IUPAC system in organic and inorganic chemistry is different. In case of inorganic or especially in coordination compounds, we have different IUPAC rules and regulations. In case of organic chemistry, carbon is there. So accordingly, carbon we are going to nominate. The functional organic functional group also present in there. So in case of coordination compound, we talk about nomenclature. The formulas and names adapted for the coordination entities are based on the recommendations of the International Union of Pure and Applied Chemistry, that is IUPAC. The following rules are used when naming coordination compounds. The cation is named first, both positively and negatively charged coordination entities. It means that we have to write the name of cation first. If it is present as a counter ion, that is called cation, both in positively and negatively charged coordination entities. Whether coordination entities contain positive or negative charge, we have to write first left hand side counter ion if it is present in the complex. Like in next, the ligands are named in alphabetical order before the name of the central atom or ion. It means that ligands to be taken in alphabetical order. name of the anionic ligands ends in O. Those of the neutral and cationic ligands are the same except aqua for H2O, amine for NH3. It means that whenever the H2O is coming, we have to write aqua, not water. That is aqua. Chemical name of water is aqua. In case of NH3, it is amine. In case of CO, that is carbonyl. And in case of NO, that is nitrosyl for NO. While writing the formula of the coordination entity, these are enclosed in A brackets. That depends upon how many ligands are just coming with the metal. Prefixes mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. Now, when the name of the ligand include a numeral prefix, note down this point, this situation becomes important sometimes in examinations also. When the name of the ligands including numeral prefix, then the term bis for 2, tris for 3, tetrakis for 4 are used. The ligand to which they prefer being placed in parenthesis. Like example, NiCl2 PPH3 whole twice. PH means phenyl, is like benzene ring -1 hydrogen, that is called C6H5 called phenyl, or generally written as PH. NiCl2 PPH3 whole twice, that is named as dichloro, that is for Cl2, dichlorido. Bis is coming because here PPH3 is coming 2 times. That is already triphenyl. Tri is numeral prefix here. Triphenyl, numeral prefix 3, that is triphenyl. That is why we are using bis. PPH3 coming 2 times and starting of PPH3 name is triphenyl. That is why tri is numeral prefix. In such kind of cases, we have to use bis, tris, tetrakis accordingly. The number of the kind of these ligands are coming. So, in this case NiCl2 PPH3 whole twice is named as dichlorido, that is for Cl2, Cl is negative, we have to write like IDO. Dichlorido, bis, triphenyl phosphine, nickel, and the oxidation state of nickel to be written in Roman here in bracket. In case of this complex NiCl2 PPH3 whole twice, we know that triphenyl phosphine is a neutral ligand and Cl is -1. So, in this case x minus 2 will be equal to 0, then x will be 2. That is why here nickel is present in oxidation state 2. So, it to be written as dichlorido, bis, triphenyl phosphine, nickel second. In further, oxidation state of metal, that we have already done in previous slides, that was in 2 in parenthesis in Roman. Oxidation state of the metal in cation, anion or neutral coordination entity is indicated by Roman numeral in parenthesis. If the complex ion is a cation, the metal is named same as the element, like it is Cr chromium, Mn manganese, Co cobalt, Pt platinum. If the complex contain positive charge, the metal name same as the element. For example, Co in a complex cation is called cobalt, and if Pt is coming, that is called platinum. If Cr is coming, that is called chromium. If the complex ion is anion, it means that contain negative charge. The name of the metal ends with the suffix ate. We have to write ate with the name of the metal. For example, Co in a complex anion, that is COSCN4 2 minus. Here the complex contain negative charge. So, cobalt here to be written as cobaltate. Metal is same, but the writing process that to be decided according to the charge present on the complex. In case of positive and cationic species, CO to be written as cobalt, but in case of anionic species like that in this complex, COSCN4 2 minus, then cobalt to be written as cobaltate. For some metals like Latin names are used in the complex anion. In case of ferrate for iron, in case of Fe the ferrate to be written. So, by this situation we must be very clear how the name of the metal to be written accordingly in the complex, that will decide by the charge present on the complex. If the charge is not able to decide, we have to ionize, look at and dissociate or ionize the complex. In case of K4FeCN6, if you want to decide the charge on the complex, separate the counter ion that is present potassium, you will get the charge on the coordination entity and name of the metal to be written accordingly. Now, next rule, that is the neutral complex molecule is named similar to that of the complex cation. Now, making it more clear, we are taking some examples. The following example is illustrate the nomenclature of coordination compounds. In case of first example, CrNH3 whole thrice, H2O whole thrice, bracket close, Cl3, that to be named as. Now, one is NH3, that is amine, one is H2O, that is aqua. Amine, aqua, AQ, that is amine. Alphabetically, amine is coming first. And NH3 present 3 ligands, aqua present 3 ligands. So, it will be written dry. We are writing the NH3 and aqua both ligands in alphabetical order. So, triamine, triaqua, chromium, third chloride. Now, look at the complex again, that is Cr, NH3 whole thrice, H2O whole thrice, Cl3. Here Cl3 is counter ion. To calculate the oxidation state, Cr to be taken as X, and we must know that identification of the ligand is very important, because NH3 is neutral ligand, H2O is also neutral ligand, and counter ion Cl3 is each contain -1. So, equation will be X minus 3 is equal to 0, then X will be equal to 3. So, oxidation state of chromium in this complex will be 3, that to be written in bracket, and the name of the counter ion to be written. How many counter ion there outside the bracket? There try not to be written, never, only write the name. So, the complex name will be triamine, triaqua, chromium, third chloride. Now, take one more example, that is CO, NH2, CH2, CH2, NH2 whole thrice. This is ethylene diamine. Ethylene diamine whole thrice, SO4 thrice is named as tris. Why tris is coming? Because NH2, CH2, CH2, NH2 is coming 3 times, and it is ethylene like diamine. So, tris ethane 1,2 diamine, cobalt, oxidation state of cobalt is 3, sulfate. In the next example, PtNH3 whole twice, Cl NO2 to be named as diamine, chlorido, nitrito, and platinum. Look at here again. NO2, nitrito, it means that we know that NO2 is a ambidentate ligand. So, N is coordinating with the platinum. That is why nitrito and platinum and its oxidation state 2 is being written here. So, by completing this one like IUPAC, we can just do the more practice. You can take different kind of examples, and definitely in the coming examination, the IUPAC name from the organic or inorganic portion, or especially in case of coordination compounds, sometimes question is coming only to calculate the oxidation number of the central metal, identify the ligands, types of ligands, and counter ion is also there, or taking two separately, IUPAC name can generally ask. One more important point can be noted here. What is more important? That is, sometimes the IUPAC name written is giving and question is asking to write its formula. There are two things. If the formula will given, we have to write the IUPAC name. If the IUPAC name is given, we have to write the formula of the complex. So, by making it practice, that is very simple, and we can write from the both sides, like complex is giving its formula, we can write the IUPAC name structure. It is giving the IUPAC name, we can presume to the, we must able to write the formula. Like in case of first example, CrNH3 whole thrice, H2O whole thrice, Cl3. IUPAC name will be given. We have to assume to the formula and write the correct formula of the complex. Like triamine, triaqua. It means that NH3 thrice, H2O thrice, chromium Cr, and third, it means that we have to set the coordination number, oxidation state of chromium 3. So, we must mind it, because NH3 is neutral ligand, H2O is also neutral ligand. It means that till yet the oxidation state of chromium is 0. How many chloride must we come to create the oxidation state of chromium 3? Think about it. How many chlorides should we come to create the oxidation state of central metal atom 3? So, Cl3 will be come automatically to giving the sense to make oxidation state of central metal 3. So, from the both sides, we are able to write, explain these two phenomena. Like from the complex structure is of formula giving, IUPAC name must be written. If the IUPAC name is given, we must able to write the formula of complex. Such type of questions generally asked in examinations. Now, we have to take some bonding concepts in the coordination chemistry. We will talk about some bonding concepts also. Bonding in coordination compounds, different theories has been given, like Werner's theory of coordination compound, valence bond theory of coordination compound, crystal field theory of coordination compounds. That is also related with the like LFT ligand field theory of coordination compounds. After that, standard theory is also given, like we have like organelle diagrams in higher level that generally explains the how kind of bonding and how the ligands is coming, and perfectly structuring what different kind of things can be discussed there. So, we are just going to discuss about Werner theory of coordination compounds. There was Alfred Werner, as a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. Werner was the first to describe the bonding features in coordination compounds. Werner in 1898 propounded his theory of coordination compounds.
So there are two types of linkages or valencies, we can say. One is
Yeah.
primary and one is secondary. How are they different from each other?
Actually, the primary and secondary valency concept, Werner has proposed and explained the primary and secondary valency concept.
Okay.
When we talk about complex, as we have taken example previously, K4 FeCN6, one is the complex we have just previously discussed, K4 FeCN6. Here, K4, it means that potassium is ionizable, and according to Werner, it is the primary valency. It is forming the primary valency, and the valency in the coordination sphere, it means that how many kind of coordination number or ligands are attached inside the coordination sphere, that will give the secondary valency. So, in coordination compounds, metals show two types of linkage valencies, that is primary and secondary. Primary valencies are normally ionizable and are satisfied by negative ions. The secondary valency are non-ionizable. These are satisfied by neutral molecules or negative ions generally. Secondary valency is equal to the coordination number is fixed for a metal. The ions groups bounded by secondary linkage to the metal have crustatic spatial arrangements correspond to different coordination numbers.
So we don't have much time
Yeah.
left. So I would request you to explain this example and maybe wrap up.
Just definitely we will just going to conclude.
Okay.
But we have to take one example in case of Werner complex.
Yes, please.
That will be generally sometimes come in examination also. So complex like that CuCl3 6NH3, that to be written in complex form CONH3 whole 6 Cl3. Here NH3 6, that is secondary valency, Cl3 primary valency, and according to Werner, the ligands which is coordinating to inside the coordination sphere to be written as dark bond, that is secondary valency, non-ionizable valency, that is NH3, and Cl3, that to be denoted as primary valency indicating, and we have to write it by the dotted bonds. It means that the complex to be written as CO5NH3 by the dark bond and 3NH3 by the dotted bonds. It means that this complex has 3 primary valency and 6 secondary valency. So, number of Cls precipitated whenever react with the AgNO3, we will get white precipitate of AgCl in this complex, that is Cl3 will be 3 Cl negative ions, total number of ions will be 4. So, by this way just we have discussed about coordination complex, we have taken kind of introduction, we have discussed about different examples, we have taken about kind of like key terms, oxidation number, valencies like that, coordination sphere, central metal atom, and especially we have gone through the IUPAC system and we gone through certain kind of rules to be followed whenever we are going to write the IUPAC name of the complex. After that we have discussed about kind of bonding theory, that is Werner's theory, and we have taken some points from the Werner and taken example. Generally we must mind to how to write the complex when in form of it is coming in Werner theory. We must be able to identify the primary and secondary valencies when the complex to be given. And one more point, that is we must also able to write the when the coordination compounds is going to dissociate or ionize, how many kind of ions to be created. We must be able to write the number of ions. Sometimes these are coming also in solution chapter, think about Vanta factor, I going to be decide. So, generally I deciding factor, we have to dissociate the complex, how many kind of ions are coming, that is also taken as an important part of there. So, by this way this example has already been discussed, and there are more things are also there. So, we will discuss these things in the coming sessions whenever we will get This is.
Thank you so much, sir, for being with us today and for explaining each and everything in so much detail. I'm sure our viewers, they have understood each and everything, and if in case they have missed watching this program, they can always watch it again on NCERT official, that is our YouTube channel. Thank you once again, sir.
Thank you. Thank you.
Thank you to all the viewers for being with us today. I really hope that you enjoyed this entire conversation. We were discussing coordination compounds, and under coordination compounds, we have discussed a lot of things, be it oxidation number, be it the valencies, the types of valencies, be it the ions, and be it ligands, and many more things. So thank you so much once again, and we are wrapping up our particular program right here, but do not go anywhere because we are showing you the schedule for Monday, and on Monday we will be bringing many programs for all of you. You can see it on your screens as well. The programs will begin at 8 o'clock. From 8 to 8:45 we will bring you our Yogshakti program. The topic of discussion is going to be yogic practices for management of diabetes mellitus, and till 5:30 we will have continuous programs for all of you, be it on various subjects, on various topics, and even the last program is going to be our Sahyog series from 5 to 5:30 for channel 6 to channel number 12, and the topic of discussion is going to be importance of imbibing values for overall development. Do watch these programs, and for queries you can always reach out to us. And before we conclude this program, I would also like to thank our sign language interpreters. Thank you so much Neetu and Rimpi for being with us and for interpreting each and every word that we discussed here. Thank you so much, and thank you once again to all the viewers. I really hope that you are going to have a great day ahead. So let me please take a leave of you. I am Tanvi Khurana. Thank you so much once again. Namaskar.